So I think we're going to transition to the next stage here, and talk about a little bit about what's going on inside of the system, right? How did you do this? What is it really, right? And how did this come about in a way that we reach these numbers? And we got into some performance numbers as well as system architecture pieces. So we saw this before, design objective. We started with a philosophy of trying to build the next generation storage architecture, realizing that we need a lot more than just storage and capability in this system to solve for these real edge case that we're talking about. We landed on this architecture. We talked about the capability and what's inside of it, and what it can hold, if you will. A big part of this design drawing here that you can see is Fabric Express, as we call it. It's essentially our internal bus that we have put together to make this possible. And the whole idea behind Fabric Express is, like we said, PCI Express is a lot faster and cheaper and built into everything to move a lot of data fast. So let's take advantage of it in a way that gives us these benefits, right? So taking a look at a PCIe and an NVMe, which is really the heart that drives a lot of these I/O capability of this subsystem, right? Do a bit of a primer on PCIe to start with, right? It's been around forever. Everybody knows the term. Not everybody digs into the details and the underpinnings of PCIe per se. It's a serial bus that has a transmit and receive that creates a lane, essentially. You then have those lanes ganging up in parallel to create a link. You can have a by 1 to by 16. The spec actually takes it all the way to by 32, but today's architecture, you see it top out mostly in by 16s, right? 8 gigatransfer a second, that means that it's 125 picosecond bit timing, right? So these bits fly really fast, and there's a lot of them running there, right? Each lane adds up to about almost a gigabyte a second in each direction. So full duplex in one lane is 2 gigabytes a second. That's all built into the chip right there, right? And we haven't really exploited all of that. So we're like, okay, let's expand on that. So essentially, 1 by 16 link gives you close to 32 gigabytes a second full duplex. And every CPU comes with it, and you're not paying any extra for it. NVMe, software side now. Okay. Intel was a really big proponent in driving the NVMe standard. Many of us recognize now why. Because they started the Nvme Protocol stuff a long time ago. And the reason for it is because if you have a media that you can access really, really fast, and you have a protocol that sits on top of that media, that takes up a vast majority, if not, frankly, at this point, we talked about 3D crosspoint media earlier. And if you're going to do 3D crosspoint accessible media over some storage interface, you're literally spending 90% of your time traversing the Linux kernel, block drivers, controller architectures, right? This is where this doesn't work. We got to break it up and do something different. This is where really a lot of the NVMe impetus came from, right? We got to create a protocol that allows for the flash performance of the capability to really come through, right? So the Nvme architecture rethought a lot of the whole I/O streaming and such, right? While the SAS and the SATA protocols had their focus on developed during the hard drive era, had its ambitious goals of the time, but just not good enough for what was going on anymore. And this is where the NVMe now comes in. So what's different about NVMe is that it is massively parallel. 64,000 queues, 64,000 entries per queue, which allows for a completely lock-free distribution of those I/O queues between the cores to give you a very low latency, high performance API. And on top of it, it is a very, very lean protocol. It is less than half the CPU cycles for every I/O. So not only is it massively parallel, but every I/O in turn also takes a lot less time inside of the CPU, right? And, well, the software latency that you lower by doing that is also impacting the end target. So if you have a SAS device, well, that controller, the SAS controller that's sitting in that SSD, has to do the same protocol handling. So the controller also becomes busy doing a lot more work. So you improve latency tremendously, right? So here's the protocol comparison we did when Intel wanted to. So Intel announced their dual-ported NVMe drive a year ago. They came out and said, hey, look at our DC3700, I think it was, is what they called it. And essentially, we have a dual-ported NVMe drive. We had built the system while they were building the device in parallel. We launched first kind of preview of our system at that time. And here's the SAS versus Nvme Protocol Impact that we ran on our system, right? And what we're seeing is roughly 6 times difference in lower latency, which of course immediately translates to 6 times higher IOPS, right? So these are radically impactful, right? So the whole idea is there's a tremendous benefit of using NVMe over PCI Express rather than 12 gig SAS, if you will. So what's this Fabric Express actually? So we take the motherboards and we extend the native PCIe bus that comes out of the motherboard into our enclosure such that we can take advantage of those lanes and attach these devices to it. So we have 6 modules essentially. These 6 modules hold up to 12 drives each. That gives us 72 drives in the system, right? And you can populate those drives, frankly, in any way you want. So if you want a lower capacity, I should say, because by the time you spread across all the data packs, if you will, or the SSD carriers here, they are adds up to becoming, 24 drives anyway, right? So it depends a little bit on how you want to configure it, but it allows us to populate them according to the need of the application, right? And it also ties the both server nodes together. That allows us to run inter-node communication over the same bus. Very low latency, very high bandwidth, right? And it also allows us to memory map each other's spaces. So we can do very low latency application semantics that does not have to take the latency of going down the Ethernet stack, out in the wire, over to the other guy, up the Ethernet stack again, and then talk to the network, right? Now we're talking low-digit microseconds to communicate between the 2 servers for metadata transactions or whatever needs to be, right?
So the 2 servers, that's strictly for HA, or is that for load balancing across?
Sure. Since it's a hardware box, you could use it any way you want. We built it clearly when we started the project with the intent for high availability, right? A high availability storage architecture that needs to have a mirroring bus for the write-back cache. Very straightforward, right? We use the PCI Express to mirror the data back and forth. Turns out, the PCI Express bus can also be virtualized in a software layer to become an Ethernet bus. Software doesn't know any different. It just goes over Ethernet or PCI Express very, very quickly. So if you have a server cluster, for instance, if you want to run a clustered logical volume manager or something like that with a transactional database on top of it, now you can have a transactional database with, double-digit microsecond access to the entire half a petabyte of the pool for the database, right? 2 clusters nodes in the same box, and all of a sudden, right, you don't need a SAN for shared data on the back end for the entire thing, right? So we also see 2 different nodes being used where one node has a certain purpose. Like I talked about before, data ingest is a hard problem when you're trying to do it fast enough on the Ethernet. And mainly it's a hard problem because management packets on the Ethernet wire, 64 bytes, they're small. And when you can stuff 40 gigabit on that wire, you can divide by 64 and see how many of them it is in a second. That's a hard problem to solve. Mm-hmm. That's why you see buffers on the cards and all that kind of stuff, right? So in those scenarios, it becomes essentially a networking probe dedicated to do nothing but peel the packets off the wire. And you can't do much else on that node. So that node now is dedicated to do nothing but take the data, put it on the media. Now you have a node right next to it that shares the same data set that you can do now fun stuff with. You can read the data, you can do analytics, you can do real-time stuff. While the other guy is writing, you can do this, right?
I can see how that solves a problem. Gus?
Go ahead.
I'm sorry, Ray. But clustering software, do you have something in place to make, say, one of these devices does go down, a failover to the other to handle the compute layer?
Right. So we rely on the software layer. In our case, when we get there and put our software on it, right? Clearly, we take care of that, right? Now, let's say that you have a cluster database. It's a shared storage backend.
No, I'm really talking more about a hardware cluster. Because a lot of the time the failover takes, particularly when the data is flowing at this kind of transfer rate, really interrupts the operations of the processing, of the ingest of.
Right.
Is there a cluster management software that takes that sort of down to a very short?
So we rely on, if I understand your question correctly, let me try to answer it. We rely on the clustering software that is available in whatever application you're running today. So let's take, in the case where you have one server running ingest and the other one doing analytics, there is no redundancy in that system. Right? Should you have one of those go down, you lost that capability. So what we're seeing when we talk to those use cases is, well, we have two systems and they do it in parallel. Should one go down, the other one keeps going. So that's what kind of their redundancy level, right? The alternative architecture that you're working with today is a server doing nothing but ingest, right? Put it on the wire, and by the time you actually want to do something, it's after the fact kind of thing. You say, oh, something went wrong yesterday. Let me go and suck out the information that is inside of that box from yesterday and do a forensics at that point. You don't get no real time at all today, right? So it's not necessarily, and by the way, yes, they have two systems running side by side doing that today, because should one go down, the other one takes over anyway. So it becomes a redundancy by independency, if you will, right?
A failover isn't something necessarily you guys provide, it's something you allow your partners to develop on. And
exactly, but it's possible to use on this architecture because of the shared data set, right? So the dual ported nets architecture allows you to create a failover because it's a shared data set. Okay?
What's the offload modules as part of the FREB Express do?
That's the GPUs.
Oh.
So the offload modules allows for...
So those offload modules could be accessed from either server then?
So in this, you have the two middle flash packs there contain GPUs. Those offload modules are essentially an extension for compute offloading, right? So you connect those into this architecture if you need more CPU. So if you look at how much CPU can you cram? Well, you know, of course, there's extreme architectures out there that cram tremendous amount of cores in a small footprint. Well, that's not really what we're trying to do. What we're trying to do is give a lot of CPUs that are cost-effective,
balanced with the rest,
coupled with this very large data set, right? So 2699s, 88 cores, 176 cores is a lot of CPU, believe it or not, right? It's actually a tremendous amount of CPU. That CPU gets you up to 3.6 teraflops, right? That's including turbo boost and all that stuff in there. Now, one NVIDIA V100 is about 15 teraflops. Two of those in there, you have multiplied your math capability, essentially, by 10. Right? So it's no wonder that we're seeing a very, very ferocious appetite for these offloading systems in the servers today, especially for very heavy computational architectures, right? So if you can figure, the drawback, of course, is, well, you got to write software to take advantage of it, and there's not a generic API that you can just drop software on top of it and it runs 10 times faster. No, you have to actually understand your problem. You have to code against this hardware to take advantage of it. But what we're seeing in the market today, right, which is also evident by NVIDIA stock, a lot more and more is figuring out how to do this effectively, right? So networking, 16-lane PCIe per server for networking. So that's a dedicated by 16 lane. This allows us to do, 2 by 100 gigabit per server easily, right? We can go even faster, but the point there is we can attach these to a very high speed network architecture as well. And yes, it can take the same RDMA enabled NICs that you see that the networks are starting to take advantage of today, right? Yeah. And that means that the software architectures for applications out there that takes advantage of those drops on, runs just like it would on any other server. Okay? We have given the ability to do a full height card in there as well. And the reason for this is because what we're seeing from these network capture architectures is that the form factor of those NICs are bigger than what the traditional half-height cards are, because while they put ASICs on there, they sometimes put FPGAs on their cards and such, so they need a bit more space, if you will. The SSD carriers, like I said, hold 12 drives per carrier, up to, and each is 25 watts. That's 300 watts in a carrier from a, let's call it spec number, right? And the GPUs are 300 watts per GPU by the spec. So it's very symmetrical when it comes to, are you running 12 drives or are you running 2 GPUs in a double wide. So from a power and footprint perspective, right, this balances very, very nicely, and we have then made these pluggable modules interchangeable that way. Make sense? Yeah. Any other questions so far? So here's some performance numbers. Small block transfers, 4K, 100% writes, 30 gigabytes a second at 4K transfers. 7.8 million IOPS, and you can see the lowest latency, 35 microseconds, goes up to 90 microseconds where we hit our 30 gigabytes a second. On reads, 33.7 gigabytes a second, bit over 8 million IOPS, and a little bit higher latency. Part of the reason for the write latency being lower than read latency is, well, these SSDs also have a write cache that is, faster to media, so the read latency goes up a little bit, okay? Large transfer.
I'm sorry, David, could you go back to those graphs?
Sure.
For a second. The IOPS numbers there those are 78, like the first one, 78K, 7.8K are doing 30 gigabytes, 30 and a half gigabytes per second, because they're big.
Right, so
they're big IOPS.
We hit 7.8 million IOPS. Latency,
oh, it's million.
90 microseconds
okay.
At 30 gigabytes a second.
Yeah, it's million IOPS, okay.
Once you saturated the link, yeah.
Right, you saturate the bus, and once you saturate the bus, you ain't gonna go any faster, right? So you can see we hit the saturation on the 4K there. On a larger transfer, 128K, we saturate the bus pretty quickly. QDEF1, we hit almost 36 gigabytes a second on reads, on writes, right? And we hit that at essentially at QDEF2 on the reads, right? And here's the beauty about the PCI bus. It's full duplex. So I can do these two at the same time. And yes, we don't get perfectly twice because there's some overhead when it happens, but we're seeing well north of 60 gigabytes a second at full duplex.
Could you go back to the prior one again? Sorry, I need to do this here. Thank you, come on.
Okay.
And it's 4K random reads and random writes that you're doing here. It's not
Correct.
Sequential or anything like
Correct,
that.
no sequential, nothing. It is uniform random. Okay?
Yeah.
And it turns out, if you do sequential or random, it makes a little difference.
It makes no difference?
Makes a little difference, a little. But
could you go to the next one then?
very little. Now, you can see the latencies on these are a bit higher. Yeah. And it's also because, well, it's a lot more data to transfer in one transfer, so now you stack these transfer back to back, right? Okay, so we talked about this use case. This is edge data analytics, right? Before, it was very hard. It was doable, but very large architectures were needed to have a very high-speed ingest, store the data at the same time you're trying to run an analytics and provide insights, right, for a large enough data pool. The only way you could do this, essentially, was a very large scale-out, slice the problem into smaller chunks, and find a way to have an simultaneous access to the data store. So you've got to store it on a SAN now, which has shared access, right? The only way to get it to SAN is to have a very fast SAN to get to these numbers. We know a company that went out and tried to solve that problem, right? The SSD went out and tried to do exactly the same thing, but attached to servers to do the same thing, right? And the numbers, not quite the same, but very similar when it comes to how much data we can move in those ways, right? The difference is we really built this out of volume, commodity parts to keep the cost down such that it can be cost effective in the industry. So to recap, 2U, converged server to storage, very different converged than the hyper-converged idea people have in their mind as a scale-out architecture, right? This gives you a very, very different use case in mind, right? High-performance analytics processing, large persistent in-server NVMe data store, very high bandwidth, and clearly capable of taking our storage software and do something really cool with it down the road. Any questions?
You didn't talk about...
There was a reflex of, do I really want to know how much this might cost?
So, I mean, you didn't talk about NVMe over Fabric or anything like that. It's potentially possible because you've got the networking to do that sort of thing.
There's nothing prohibits us to participate in the same NVMe over Fabric enabled hardware capabilities, right? You take an NVMe over Fabric enabled Mellanox card or so, put it on the front end, and all of a sudden, what do you have?
And the storage, I'll call it personality, runs in Linux, or what's the operating environment?
So most of the stuff that we talk to, most of the customers and solutions that we talk to are Linux oriented, very many of them. Now we have started to talk about some interesting use cases, taking Microsoft and storage spaces direct on top of this architecture, because it essentially gives you a hyperconverged software stack out of the box, right? Yeah. And if you can imagine now, RDMA enable Ethernet between boxes of this capability using that software, there's a very powerful scale-out architecture story there, right?
And the storage software that you runs at kernel mode or user mode, or?
No software.
I'm sorry?
No software. You boot Linux, it shows up in /dev/nvme, the same inbuilt into Linux kernel. So it's absolutely nothing but just
what about the write-back mirroring and all that stuff?
That's all done in the drive. Individually in the drive. They have their own write caching inside of the drive. Essentially, this is take the data out of the Linux kernel as fast as you can, shove it down the drive because it takes care of the rest, and you're done.
So if I wanted to use some kind of software layer data protection, do a Linux level RAID?
Absolutely. So you have logical volume managers, you have MDADM, you have all kinds of different things in software that can take advantage of it, right? Now, clearly, to your point, Ray, is there opportunities to take this architecture and provide services and layers on top of it to provide either kind of capabilities? Absolutely, right? And what you will see here in the talk here soon, it will be one of the things that we anticipate we can add services with has to do with how you shrink the data set with dedupe, right? Okay?
So before Gus finishes, Eric, I want to address something you just said about price.
Yes.
So I don't want to go into exact pricing because we could be on a rat hole, but if you were to go to a large, well-known server and storage, recently joined company, and spec up a server with an equivalent amount of just standard flash, you're probably going to be around the same pricing. A little bit fraction more for this, but we're not talking crazy money. When you look at some of the things that specialists that are out there like DSSD, this is a fraction of the price. So yes, it's not cheap, but it's not actually surprise you how cost efficient it is.
All the cost of the flash anyway, right?
The reality is
this,
if you need to solve a problem of this magnitude, you're going to have to solve it somehow. Any alternative architecture that has the need for this type of flash and performance will be more expensive. I can guarantee you that right now.
If you build it out of traditional architecture,
exactly
you will be more expensive. You just got more boxes, more PSUs, like everything.
Exactly.
So is there going to be reference architectures to go to said server storage architecture company and build this stuff, layering the Axellio software on top of it?
So there's a lot of interesting conversations going on. We'll see where it takes us. Right now, we are trying to help those who have this need solve their need as a system integrator. You saw Gavin's slide on how we take this to market right now, and that is, frankly, through providing this as a platform for those companies to take it to market, right?
Oh, yeah.
And as that develops, I wouldn't be surprised that conversations develop as well.
It's difficult for us not to think 2 steps ahead.
Yeah, totally understand. Totally understand.
So,
okay.
Yep.
Yeah.
Can I ask one more real quick? I guess I'm kind of the VAR partner guy in the room, but do you see this as being sold to, integrators to figure out how to wrap their stuff around it?
Very much.
And so do you see this being sold by your standard VARs and trying to figure out how to do a Splunk solution out of it or something else?
I would assume that would develop towards that. What we're seeing is people that have really tough data problems to solve are knocking on our doors and saying, hey, I heard about this thing. Can we have a conversation? We sit down, have a conversation. It usually starts with a POC. We run some tests, figure out how they're going to take it to market, right? And depending on their routes to market, right, we then work with them on that.
Yeah, to me, this is a really interesting platform. It's very different than what I expected to hear when I walked in. But it's going to be a really hard message to control properly, I think.
Yes.
And be careful how you
And this
go
is why I
about that.
emphasize, is this hyper-converged? Well,
Yeah.
I guess depends on what you think is
Definition.
hyper-converged, right?
It looks like,
Right?
but the use case is really different.
Yeah, exactly.
And the reason for it, because hyper-converged today are applied where it's very easy to scale out because of the problems they're trying to solve for are, like we talked about, embarrassingly parallel, right? And we believe that we can solve those problems more cost-effectively if you have a big enough problem as well, because the reality is just the infrastructure cost alone in some of those large deployments are tremendous, right? So we're going to start by solving some really tough problems and then move on from there.